In this session, we're going to see what one-to-one functions are. One-to-one functions are a subcategory, if you will, of functions. We can describe them by saying that a function f is one-to-one if neither inputs nor outputs are repeated. To be a little more formal, we can give a definition here. F is a one-to-one function if f of b equals f of a implies that a equals b for all a and b in the domain of f. Okay, that's pretty formal. Let's look at a graphical description and then we'll see what we've just read. Graphically, a one-to-one function passes both the vertical and the horizontal line tests. And we'll see what all this means in just a minute. Let's look up back at the definition that we just saw. F is a one-to-one function if f of b equals f of a implies that a equals b for all numbers in the domain. What this is saying is if you have two outputs that happen to be equal, it must be the case that the two inputs actually were equal. And so for a one-to-one function, we won't have two inputs that go to the same output. That's what's meant when up here where it says if neither inputs nor outputs are repeated. Saying that a one-to-one function passes both the vertical and the horizontal line tests is basically saying the same thing. The vertical line test is what makes it a function. If a graph also passes the horizontal line test, that's what makes it a one-to-one function. Before we blow a gasket, let's see what it is that we're talking about here. Here we have three graphs. I suppose I can label them A, B, and C. A, being a parabola that opens sideways, is not a function because it fails the vertical line test, right? A vertical line touches the graph in more than one place. And so the graph of A is a relation, but not a function. That's not new. For the graph of B, which is actually a cubic function that kind of wiggles up and down as you can see, vertical lines only touch the graph in one spot at a time. And so the graph of B is a function. But it doesn't pass what we call the horizontal line test. And as you may have guessed, the horizontal line test is like the vertical line test, but with a horizontal line. If a horizontal line crosses the graph in more than one place, then we have something that's not a one-to-one function. Now let's see what this has to do with the definition that we just saw. If we were to give a list of ordered pairs here, then for this particular horizontal line, we have outputs that match when inputs don't. In other words, I could have an XY table with values like x1, x2, and x3, and the outputs would all be the same. In that sense, the outputs would be repeated. Just as in A, we would have inputs that are repeated, and that's characteristic of failing the vertical line test. So the horizontal line test indicates that whether or not we have a one-to-one function. In C, we have another cubic function, but this one doesn't wiggle so much. We have a graph that passes the vertical line test, and so it's certainly a function, and it passes the horizontal line test. No horizontal line will touch it in more than one spot. Therefore, the graph of C is the graph of a one-to-one function. So we can kind of visualize all of this stuff in kind of as a set diagram here. So we have this class of things called relations. As we've seen, those are simply a mapping between two sets. Inside of the relations, we have these special relations that are called functions, where each input goes to only one output. Inside of the group called functions is a special class of functions that are called one-to-one functions that pass both the horizontal and vertical line tests. Sometimes we can use the expression that defines a function to figure out if it's one-to-one. Not always, but sometimes. Here we're told to determine if f of x equals 2x plus 3 is one-to-one. That is it a one-to-one function? It's certainly a function because we have it in function notation. And what we're going to do is we're going to suppose that f of b is equal to f of a generically, and then see what we come up with. Let's look back at our definition so that we'll know how to interpret what we're doing. Our definition said, if f of b equals f of a implies that a and b are the same for all a and b in the domain of f, then f is a one-to-one function. So we're going to set f of b equal to f of a and see if we're forced to conclude that a equals b. F of b equals f of a, well, if f of b were to equal f of a, then that means that the outputs are the same, right? F of b, using function notation for f of x equals 2x plus 3, is 2b plus 3. F of a is 2a plus 3. And now we just kind of tinker with it. We're not solving for anything in particular, really. But I guess we can say we were solving for b. What the heck? I guess that makes it easier. If I'm solving for b, then I can subtract 3 from both sides and end up with 2b is equal to 2a. Dividing by 2 gives me that b equals a. And so we started with the assumption that f of b equaled f of a, and we ended with the conclusion that b equals a. This means that f is a one-to-one function. That's what we're looking for in order to be able to say yes. F is a one-to-one function. Next, we're given a different function, same directions. Determine if g of x equals x squared plus 2 is one-to-one. We're going to start the same way. We're going to assume that g of b is equal to g of a. Well, g of b is going to be b squared plus 2. G of a is going to be a squared plus 2. And what we're looking for is, are we forced to conclude that b equals a? So let's solve for b. Subtracting 2 from both sides gives us that b squared is equal to a squared. If I then square root both sides, then we might think we're home free, but we have to remember if we square root both sides of an equation, there's plus or minus. Therefore, what we conclude is that b is either plus or minus a. So b could be a, but b could be negative a. I'm not forced to conclude that b equals a. Therefore, g is not one-to-one. Sometimes we use the words 1, 2, 1. Sometimes we just use the symbols, like the numerical symbol. 1 looks like 1 minus 1. Let's look at this from a graphical standpoint. I'm looking back up at f. F of x equals 2x plus 3 is a linear function. Crosses the y-axis at 3, and it has a slope of 2. So you can see that this function here passes both the vertical and the horizontal line tests, thereby reinforcing that f is a one-to-one function. The graph of g, if you remember your library of functions and transforming them, is a parabola. His vertex is 2 units up on the y-axis. I see that g passes the vertical line test, but I also see that g fails the horizontal line test. For any particular output, we can have more than one input associated, thereby making it not one-to-one. For our last example, we're given a function h of x is equal to x cubed minus 7, and we're asked if it's to determine if it's one-to-one. So we start with assuming that h of b is equal to h of a. If that's the case, then b cubed minus 7 would equal a cubed minus 7. Solving for b again. We're going to add 7 to both sides. We have b cubed is equal to a cubed. When I cube root both sides of an equation, I don't have the plus or minus. And so here I'm forced to conclude that b is equal to a, meaning that h is 1 to 1. Graphically, h is a cubic function that's been moved 7 units down on the y-axis, and so passes both the vertical and the horizontal line tests. And again, the graph is just confirmation. Your work would be the algebra that we just did.